pick up a question.
Hi, this is Gregory Aboud. About 20 years ago, there was this technology called Enodo, and it was a pattern that could easily be printed on a piece of paper that would give you the location on the piece of paper, and there was a pen with a tiny camera that, so when you wrote on it, you could know where you were writing. So I'm not saying that what you're presenting is not novel. I'm just saying it gives an idea for how you might have a surface that would not only you'd be able to determine that you're on a table, but you'd know exactly where you were. So imagine in a restaurant being able to put your smartphone on the table and it would pull up the menu. It would also know where you're seated so you could order and whatever. So I think you should look at the Enodo technology and see how you might leverage your microcam for those kinds of applications. Well done.
Thank you, thank you. Yeah, I will look at it. Thank you so much.
Yeah, thank you for great comment, Gregory. Okay, so let's move on. Could you switch the video? Okay, great. All right, so our sixth presentation is from now on. It's ISWC notes, and our presenter she barely needs introduction, but just I'd like to introduce her anyway for newcomers. So this presentation will be presented by Professor Lucy Dunne. She's a professor at the University of Minnesota at the College of Design, and she is a 20-year ISWC veteran. Her research interest includes the design and manufacture of e-textile, garment form sensing and actuating, and human factors of wearable systems. And she's presenting this work on behalf of her the PhD student, Alireza Golgouneh, and who was unable to attend, unfortunately. And another unfortunate thing is that he is already hired.
All right, thank you. Yes, unfortunately, Alireza could not be here because he's in the middle of his first week of work at 3M. So you can't hire him, but keep your eye on him. He's great. And I won't read you this title because I think we got the award for the longest title. But I'll jump right in. Today, I'll be talking about the problem of sensing compression on the body. And in our lab, we do a lot of on-body force. Well, we need a lot of on-body force sensing, partially because we do a lot of active compression. So we make devices that squeeze the body in different ways for different applications. But also because we're often in the position of wanting to be able to sense what's happening to the body because of something that's worn on top of it. And if you've never worked in force sensing, this seems like a really trivial problem. You buy a force sensor, you put it on the body, you sense things, everything's fine. But like many problems in wearables, it's not quite as easy as it sounds, and this paper is a lot about illustrating why. So if you want to sense something that's applying force to the body, you would typically take a force sensor and put it onto the skin. And then the force is applied to that sensor. The challenge here is that the first thing that happens is that the sensor gets deformed. You know, it starts out as a planar object, and then it gets wrapped around some body segment. And then sometimes the force that's applied to it also deforms it, but I won't get that far in this paper. Unfortunately, most force sensors are sensitive to both that curvature and the applied force. So the curvature itself is inducing some error in the sensor. So what happens is you end up with force that's either under or overestimated. And here, our hypothesis is that if you added a bend sensor, then we might know something about that curvature. We might be better able to model the resulting sensor signal and be a little bit more accurate in measuring force. So what we did, we tested 4 sensors. 3 of them are custom-made soft e-textile sensors that we make in the lab. And the 4th is a commercial force-sensitive resistor. So you know, the reference point is what people would usually buy, and then we're also comparing these more novel e-textile sensors against that. We tested them in an Instron force applicator that measures forces and applies them. But we had to adapt the machine to be able to simulate on-body conditions. So the flat surface over on the right is the sort of control condition. This is what most sensor characterization assumes. And then to simulate body curvatures, we developed these 3D printed applicators and backplates that are engineered to represent 3 different body curvatures based on the ISWC anthropometric survey. So C2 represents the average wrist curvature, C4 is the knee, and C5 is the thigh. For each sensor, we applied force up to 80% of its saturation and loaded them and unloaded them for 3 cycles iteratively. Then we used that data to generate and test some models. So first we modeled converting resistance to force using 3 different models: an exponential model, a 1-layer MLP neural network, and a recurrent neural network. Then we tested the question of, can we use that flat model to measure curved conditions, which we obviously know is not really that great, but to measure the error that is generated that way. Then we tried adding curvature information into that model, and again, I'll mention that for steps 1 and 2, we only used the recurrent network for reasons I'll show you. And then we compared the results. How much better does the model get when you add the curvature information? Okay, so this is what the baseline characterization looks like. This is no curvature, the flat condition, just modeling resistance using the 3 different methods. And you can see that the recurrent neural network works the best, mostly because it's the best able to account for the hysteresis that's present in all of these sensors. You can see in all of the charts on the right that they all represent some hysteresis, and the recurrent neural network is best able to compensate for that. It gets error down to somewhere between 1% and 6%. But then when we apply that model to the curved conditions, things get a lot worse. So we start to see errors of, between 26 and 46%, which is really not great for sensing. This kind of encapsulates the problem that we're trying to solve. And we see that error increases with the degree of curvature, which is also to be expected. Overall, we're underestimating force by quite a lot. So then when we add curvature in, things get a lot better. We drop our error down to about 1% for the best case soft sensor, and for reference, the commercial sensor is around 4%. Okay, so just to summarize, the force sensing on the body, hopefully I've convinced you that it's harder than it seems. 2 of the 3 of our low-cost and customizable e-textile sensors performed better or as well as the commercial FSR. The recurrent neural network is the best able to account for the kind of hysteresis we see in this kind of sensing, and incorporating curvature, as expected, reduces error a lot by up to about 40%. So I will say thank you to our team. The 3 of us on the right are here, and unfortunately, Alireza couldn't be here.
All right, thank you for great presentation. While the laptop is being switched, we can take one quick question.
Hi, yeah, thank you for the talk. Any reason why you started with like FSRs? Like, did you also consider some kind of 2D force sensors like the electrotomography based sensors?
We use the FSR because it's the most commonly used first choice. It's what people go to immediately when they try to do wearable force sensing, and most common in like the papers that we see. So it was just sort of a off-the-shelf, easily accessible reference point.
I see. And using your developed system, at least there's some hope that FSRs can also scale to 2D surfaces without requiring a new fancy sensor, correct?
Yes, I should note that we, as I mentioned in the beginning, we did not account for the realities of things like when you apply force to a force sensor, you also deform it.
Okay.
So especially localized forces. So I think there's more to be done, but this is a step towards understanding, A, that force sensing is not trivial on the body, and B, here's a way that we might be able to get rid of some of the error.
Okay, sure. Thank you.
Thank you. All right, let's move on to our 7th presentation. Okay, our presenter is Robert Pettis Baker. He is a PhD candidate